Techie here, AI Tech Hub. Welcome back to another explainer. So today we're unpacking a surprising and honestly kind of terrifying reality in modern software engineering. We are so conditioned to celebrate a successful deployment, right? You know, the green lights, the passing tests, the whole seamless rollout. But what if I told you that a successful deployment isn't always what it seems? Because in the world of artificial intelligence and machine learning, those green lights, well, they can be incredibly deceptive. Let's look at why.
A deployment can succeed perfectly and still be quietly wrong. I really want to emphasize those two words, quietly wrong, because they represent literally one of the biggest headaches for engineering teams today. This invisible failure is exactly the gap between traditional DevOps and modern MLOps. You see, in traditional software, if something breaks, it's usually loud. An app crashes, a server goes down, alarms go off. But with machine learning, your system can be humming along perfectly from an infrastructure standpoint, while the actual intelligence inside it is just silently failing.
Section 1. The core difference. Okay, let's dive right into this and break down exactly how our traditional success metrics are completely failing our machine learning models.
Think of your infrastructure like an airport control tower. On the DevOps side of things, the entire job is to keep that control tower running flawlessly. The power's on, radar screens are up, communication lines are open. Code deploys, and absolutely nothing crashes. It is all about keeping the planes in the air. Now contrast that with MLOps. You still need that exact same control tower running perfectly. You still need that 100% uptime. But here's the kicker. The control tower is totally fine, but the planes themselves, they can actually start to drift completely off course over time. MLOps is about realizing that just keeping the system online isn't enough. We have to make sure the intelligence driving the whole thing hasn't lost its way.
What's really fascinating here is the sheer mystery of it all. Real-world accuracy silently degrading while the system reports that everything's fine. If you remember our previous explainers on DevOps, we talked a lot about standard server health checks. You ping a server, it responds with a 200 OK, CPU usage is at 40%, memory looks great, your dashboard is totally green. DevOps says, awesome job, everything is fine. But your machine learning model? The world around it has completely changed. User behavior shifted. The data it's seeing today doesn't match the data it was trained on last month. So its predictions are just getting worse and worse by the minute. It's silently degrading. And those standard infrastructure health checks, they will completely, 100% miss a failing model.
Section 2, real example. All right, we understand the theory. We know there's a gap. But let's shift from theory to practice so we can see what this accuracy drift actually looks like in the wild. Imagine you're running a massive financial application. This perfectly illustrates the nightmare scenario I've been talking about. Look at the system state. You've got 100% uptime, 0 errors. The API is lightning fast. Your DevOps pipeline did its job flawlessly. But then, compare that to the model state. The actual business objective of this code is to catch fraud, right? And the accuracy of that fraud detection just dropped from a stellar 99% all the way down to a dismal 75%. Why? Well, maybe fraudsters changed their tactics overnight. Maybe consumer spending habits shifted because of a big holiday. The code didn't break, the infrastructure didn't break, the world changed, and the model drifted. So you have perfect code, perfect uptime, and massive business failure. This brings us to how we actually build these systems, and we've explicitly covered this in our past explainer on GitHub Actions. The standard DevOps pipeline is this beautiful, efficient, but very finite straight line. Step 1, build the code. Step 2, test the code to make sure there are no bugs. Step 3, deploy it to production. And traditionally, in a pure DevOps world, this is where the job ends. You celebrate, grab a coffee, move on to the next feature. Once it's deployed and running, you just maintain the servers.
But let's see how this pipeline expands in the machine learning world. We still have build, test, and deploy. We definitely still need all of that. But to catch that massive drop in fraud detection accuracy we just talked about, we need some serious heavy lifting after deployment. As we discussed in our ML Flow explainer, you have to add step 4, monitor accuracy. You need to constantly compare the model's predictions to reality. Step 5, detect drift. You need automated triggers that actually sound the alarm when that accuracy inevitably starts to slide. And step 6, retrain. You have to feed the model new data so it can adapt to the current reality.
On a loop, forever. I actually want to just slow down for a second to let the weight of those words sink in. Forever. Unlike traditional software that you can kind of just deploy and forget until a bug pops up, machine learning models are basically living, breathing things. They degrade naturally just by existing in a changing world. MLOps is not a one-time deployment process. It's a continuous, never-ending, living cycle of monitoring, learning, and adapting. Literally, if you stop the loop, your model dies. It really is that simple.
So what does this all mean? I want to leave you with a bit of a provocative question. Is your perfect code right now hiding a drifting model? Are you looking at a green dashboard while your system is quietly making wrong decisions? It's a little terrifying to think about, for sure, but acknowledging it is the very first step to building truly resilient AI systems. If this explainer sparked your curiosity and you want to understand exactly how to set up those automated tripwires to catch bad predictions, drop a comment with the word MLOps down below, and we will take a much deeper dive into drift detection next time. Thanks so much for learning with me today, and I'll see you in the next explainer.